Right now we're going to review some problems that have to do with logs. Well, there's two ways to think about this. One way to think about it is, well, 3 to some power equals 3 to some power. Those two powers better be equal. So we could set 3x minus 2 equal to 5 minus 2x. Another way to do it would be to say, hey, let's take the base 3 log of both sides. And I picked the base 3 log because 3 is the base of this exponent. And what happens when you take the base 3 log of 3 to some power? Well, the answer is just the exponent. So then we get 3x minus 2 equals 5 minus 2x. And then we can just solve this. Add 2x to both sides. We get 5x minus 2 equals 5. Add 2 to both sides. And we get 5x equals 7. Divide both sides by 5. And we get x equals 7/5. So that's how we would solve for x in that case. How would we solve this ugly thing for t? Well, t is in the exponent here, so we're going to have to get this power all by itself first. So let's start by adding k to both sides. Then we get c plus k equals b times a to the t over d. Now, in order to get the power by itself, we need to divide both sides by b. So then we have c plus k over b equals a to the t over d. And we're going to use the same sort of trick we did last time. When we have a base that we want to get to the exponent, we're going to take the log with this base. So we are going to do the base a log of both sides. And the reason we do that is because it works out nicely on this side. The base a log of a to the t over d is just the t over d, the exponent comes out to the front, t over d times the base a log of a. The base a log of a, which is just 1. So that's just 1. So t over d times 1 is just going to be t over d. And then over here we have the base a log of c plus k over b. And now to get d by itself, all we need to do is multiply both sides by d. They'll cancel here. And then we get t equals d times the base a log of c plus k over b. Ding! Okay, so here we're going to get back to what's the definition of a log. A log is the exponent that it takes to get this base up to this power. So 4 to what power is 16? 4 to the second power is 16. So this log is equal to 2. And then 4 to what power is 1/4? That one might not seem as obvious. 4 to some power equals 1/4. Well, that's the reciprocal, right? So that's 4 to the negative 1 power equals 1/4. So this log, 4 to the negative 1 power, is 1/4. So this whole expression is equal to 2 over negative 1, which is negative 2. Ding! Okie dokie. Now on this one, this is like the first problem we did. The base 5 log of this equals the base 5 log of that. Then this must equal that. Another way to think of it is if we did 5 to this power and 5 to this power, 5 to the base log 5, those will cancel each other out, and we get 3x minus 15 equals 5x minus 23. Okay, so let's solve for x. Subtract 3x from both sides. We got negative 15 equals 2x minus 23. Then we're going to add 23 to both sides. And we get 8 equals 2x. Okay, so divide by 4 and we get, divide by 2 and we get x equals 4. But something about logs is we have to be careful. Remember, the original equation was a log equation. And we have to make sure that this solution is valid. So what we're going to do is we're going to plug it in. The base 5 log of 3 times 4 minus 15 equals the base 5 log of 5 times 4 minus 23. So this is the base 5 log of 12 minus 15 equals the base 5 log of 20 minus 23. So we get the base 5 log of negative 3 equals the base 5 log of negative 3. So you might think, oh, nice, they're equal. But then you have to remember that, what is a logarithm? And what's the domain of the log function? This means that 5 to some power equals negative 3. Well, can you raise 5 to any power and get something negative? What power would I raise to get something negative? Well, maybe you might think, oh, a negative power. Well, if we put like a negative 2 in there, what does that really mean? That just means 1 over 5 squared. That doesn't become negative. That's 1 over 25. There's no exponent that you can put on 5 that will give you a negative answer. So this solution is extraneous. Which means that there's no solution to this equation. Unfortunately, there is no solution. Alright, so this is the equation that tells us the decibels of a sound, where I is the intensity of the sound and I0 is the lowest intensity that can be perceived by the human ear. So how many times bigger does this sound intensity have to be than the minimum sound in order to be 140 decibels? So I'm going to plug 140 in for D. 140 decibels is 10 times the base 10 log, which you don't really have to write the base 10. It's understood if you write no base that it's base 10, because our world is pretty much base 10. All right, so to get the log by itself, we're going to divide both sides by 10. And we get 14 equals the base 10 log of I over I0. And then, so we're remembering that the base is 10 here. How does a log go? It's 10. This is the base. If we want to switch this into exponential form, which is how the only way we're going to be able to solve this, 10 to the exponent, which is 14, equals this. So 10 to the 14th power equals I over I naught. And then if we were to multiply both sides by I0, we would get I naught times 10 to the 14th power equals I, which means that I is 10 to the 14th times bigger than I naught. So the answer to this one is 10 to the 14th. Hope that helps. Give me an email if you have any more questions. Talk to you later. Bye.